In this video, we're going to be talking about definitions of continuity. It's important that you understand the definition of a limit in order to follow along with this video. The definition of continuity has three parts, and all three parts have to be true in order for us to say that the function is continuous. The first part is that the function has to be defined for all values. For any input that I plug in, I have to get an output. I can't have any undefined values or discontinuities. The second part is that the limit has to exist. And the definition of a limit says that the left-hand limit and the right-hand limit have to be the same in order for the limit to exist. So no one-sided limits there. The third part simply says that the first and second part have to be the same. So whatever my function is defined at for an input has to be the same value as if I try and evaluate the limit at that input. So the limit value and the value of the function defined at that point have to be the exact same thing. If a function is continuous at a given point, then the limit exists at that point. That's just a given. If a function is continuous, we know the limit exists. If we try and flip that statement and find the converse, though, that's not true. It doesn't hold up. We can't say that because the limit exists, the function is continuous. And that's an important discrepancy. When does this happen? When does a limit exist, but the function is not continuous? Well, it happens at what are called removable or point discontinuities. Let's look at this example. In the graph, we can evaluate the limit. If I try and find the limit as I approach -1, from the left, my limit value is approaching 1. If I evaluate my limit at -1 approaching from the right, my limit value is also 1. So I know the limit exists because the left hand and the right hand limit are the same value. However, if I try and evaluate my function by plugging in -1, it's telling me that I have an undefined output. So that's a hole. This is not continuous even though the limit existed. Similarly, over on this example, this is a different type of point discontinuity or removable discontinuity. I can evaluate the limit. I can approach +2 from the left. My limit value is 2. I can approach +2 from the right, and my limit value is 2. The left-hand and right-hand limits are the same, so I know that the limit exists. However, if I try and evaluate the function by plugging 2 in, I'm told that the output value or defined value is actually 4. So because the limit value of 2 and the function value of 4 are not the same, this is not continuous. There are other types of discontinuities. They're called non-removable discontinuities. The first example is called a jump discontinuity. And the name is really descriptive of what happens in the graph. If you look here, we're going along at -1, and then all of a sudden, when I try and plug 0 in, I hop up to 1. So this is called a jump discontinuity. Here is the function that gave us this graph. This is just one example, not all of the examples. So a jump discontinuity is described when the left-hand limit doesn't equal the right-hand limit. We're jumping there. The second type is called an infinite discontinuity, or sometimes it's called an asymptote discontinuity. We need to be careful when we're describing this because the definition of a limit says that it exists if the left-hand limit and the right-hand limit are the same value. And it may seem that that is true here. On the left hand, the limit is approaching positive infinity. On the right hand, it's also approaching positive infinity. But because we're approaching infinity, we say that it's unbounded. The output is unbounded. We can't define infinity. Therefore, we can't say that infinity is a possible limit value. Another type of discontinuity is called an oscillating discontinuity. And these happen specifically when we're talking about trig functions. Anytime I see an undefined trig value, we start to see this oscillating behavior in the graph, and it gets really hard to read. So oscillating discontinuities happen specifically in undefined trig functions. Let's do some examples where we talk about intervals on which a function is continuous. And if it's not continuous, we're going to describe what's going on. We're going to talk about the x value at which there's a discontinuity and we're going to talk about the type of discontinuity. Some functions are continuous everywhere. Linear functions, quadratic functions, polynomial functions to the nth degree, cubes and fourths and so on. They will always increase or decrease continuously. So anytime you see a linear, quadratic, or polynomial function, it's always best to look at the graph, but they are always continuous. So to describe a function that is always continuous, we can use interval notation and say negative infinity to positive infinity using parentheses because we cannot contain or define infinity. Or we could say it in words. It's continuous everywhere. Here's another example of a piecewise function. This gets a little bit trickier. One thing we could do is look at the graphs of each of these functions individually, see where they overlap, and look at the described domain. We could sketch them out. Sometimes with piecewise functions, we get these jump discontinuities. Other times we may just have a hole, but we always got to try and plug these values in. So on the left here, we have a decreasing linear function that exists for any inputs less than or equal to 2. If I plug 2 in, I get -4. So +2, -4 is the last point on this graph. It's a closed circle because it's defined. The graph on the right here is another decreasing, but decreasing in a less of a slope. And that exists for input values that are greater than 2. So right here at 2, we have this possible discontinuity. If I plug 2 into the bottom function, I get -2 minus 1, which is -3. So 2, -3 is the point there. That's an open circle because really 2 wasn't included in that graph. I just wanted to test it and see what happens. When you plug this overlapping point into both piecewise functions and you get different resulting outputs, you know it's a jump. It depends on the definition here, so be careful. They don't always look the same. So to describe that, we know that this graph is continuous everywhere except for right at this point where we have a jump or non-removable discontinuity, and that's happening at x equals 2. One more example here. This is a rational function. With rational functions, we want to factor and see if we can find out any information about the graph algebraically. So I'm going to do that down here. If I factor the bottom, I get x minus 3 times x minus 2. And we can see that x minus 3 here are common factors. They're to cancel, and that's going to create a hole in our graph at x equals 3. That would be a removable discontinuity or a hole, and it's happening at x equals 3. With those canceled, what's left is -1 over x minus 2. And the bottom of a fraction is undefined if the bottom is 0. So what makes the bottom of that 0? What makes x minus 2 0 would be a +2. We know that creates a vertical asymptote or a non-removable infinite discontinuity. And that's happening at x equals 2. And we can verify by looking at a graph. We see that there's a vertical asymptote at x equals 2. The holes are not always going to be described in a graph. You're going to have to look on a data table to see that that value is undefined. So good luck describing continuity and describing any points at which discontinuities happen and describing the type of discontinuity.